In section 3.2, we're going to continue working with graphing linear equations. And we want to go ahead and graph the linear equations in the coordinate plane that we discussed in 3.1. Our new key vocabulary is standard form of a linear equation and what is a linear function. So let's talk about that really quickly. So an equation in two variables, 2x plus 5y equals 8, is the solution of an equation in two variables, x and y, will be an ordered pair that produces a true statement such as 8 is equal to 8 when the values of x and y are substituted into the equation. So that's what a solution is. A solution is an ordered pair that makes the equation true. Okay, a graph of an equation in two variables is the set of all points in the coordinate plane that represent the solutions of the equation. If the variables in an equation represent real numbers, one way to graph is to make a table of values, which we've done before, plot enough points to recognize a pattern. Sometimes we can tell exactly what type of shape it will make by examining the equation. And sometimes we need to get a little more information before we know. So you want to plot enough points, that's the key thing, enough points to recognize the pattern, and then connect the dots. When making a table of values, this is true anytime you're going to graph something unknown, choose convenient values, right? Make it easy on yourself. Include negative values, 0, and positive values, right? What does this equation do when the input is negative? What does it do when the input is 0? What does it do when the input is positive? Helps you identify what type of an equation it is. So if we look at this, and I wanted to go ahead and start plotting this graph, I'm going to try, say, -2, 0, and 2. All right, so I've got a negative number, I've got 0, and I've got 2 for my x values. Right? When I plug in -2, I'll have 3 times -2 plus 2y is equal to 8. 3 times -3 is -9. I'm sorry, that's -2, my mistake. 3 times -2 is -6. So I'll have -6 plus 2y is equal to 8. I'll add 6 to either side, so this will become 14. And divide by 2, y would be 7. So if we take a look at, actually let me go ahead and put some nice axes in here. Right, so if we look at that point, -2, 1, 2, 3, 4, 5, 6, 7. There's my first point. When I plug in 0, 3 times 0 is 0. So 2y is equal to 8, therefore y is equal to 4. 1, 2, 3, 4. And when x is 2, 3 times 2 plus 2y is equal to 8. 3 times 2 is 6. When I subtract 6 from either side, I'll get 2y is equal to 2. So when x is 2, 1, 2, y is 1. And you can see that these put themselves in a line, which is why we know that this is a linear equation. So linear means that the graph is going to make a line. Okay, so this was graphing with a table of values. I'm sorry I didn't write this last number in. So I picked negative number, 0, positive number, plugged them into my equation to create the ordered pairs that allowed me to see that this was indeed a straight line. Okay, another thing that's important for you to know is that sometimes we have these types of linear equations that aren't quite in this standard form. This is the standard form. Ax plus by is equal to c is called standard form. But we have some special cases. We have the special case where our equation says y is equal to some number. That basically means it doesn't matter what x is, y is always this number. That makes a horizontal line. And the other special case is x is equal to a number, and in that case, it doesn't matter what value of x I plug in, right? What sorry, it doesn't matter what value of y I have, my x is always the same number. Okay, and that makes a vertical line. Okay, so let's take a look at graphing things like that. If I want to graph x is equal to 2, first I'm going to go ahead and put in my axes. And then x is equal to 2, here's x is 2, and that's going to be a vertical line passing through x is equal to 2. That's what that's going to look like. Okay, equally, if I have y is equal to -4, down here is 1, 2, 3, 4. That means for all the values of x, y is going to be -4. Okay, so y is equal to creates a horizontal line. X is equal to creates a vertical line. Okay, now we're going to work with a domain restriction. So they want me to graph this linear function, and now you'll notice we're not in standard form. This is what's called slope-intercept form. Right? Remember, standard form is ax plus by is equal to c. Slope-intercept form, which we'll discuss in a future section, is y is equal to mx plus b. Okay, and that's the form we're in here. But what's important is they give me a domain that x has to be less than or equal to 0. That means I can't use any positive numbers. Okay, this has a domain restriction on it, and I'm going to go ahead then and follow that while I'm putting together my graph. So I'll want to see what happens when x is 0. I'm going to want to see what happens when x is a negative number, and just to be safe, I'm going to find out what happens when x is a smaller negative number. But you'll notice now that I'm not doing positive numbers because my domain says that x has to be less than or equal to 0. Okay, when we go ahead and plug these in, -5 times 0 plus 3 is equal to 3. -5 times -2 plus 3 is equal to 13. And -5 times -4 plus 3 is equal to 23. Okay, so I'm going to go ahead and put in my axes, but I'm going to be mindful of the fact that I don't really have anything over here to the right of the y-axis. And it looks like my numbers are going pretty high. I didn't come out with any negative results, so I'm going to go ahead and put this down so I can make the best use of the coordinate plane that I have. Okay, so when x was 0, y was 3. 1, 2, 3, there's a point. When x was -2, y was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And when x was -4, y was 10 more than that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right about there, 23. Okay, and again, this looks like it is indeed a line, but it's a very steep line. Okay, now I have to go ahead and, now this is what we're going to be, it's going to be a ray. Okay, the dot at the end is going to be solid because it includes when x is equal to 0, because this says x is less than or equal to 0. If it had just been x is less than 0, then this dot would be an open dot, and it only travels to the left. Okay, so no little pointy arrow on each end. It starts here and it moves to the left only. Okay, and that's working with graphing when we have a specific restriction on the domain. Let's solve a problem. So I'm working with a multi-step problem. The distance d in miles that a runner travels is given by the function d is equal to 6t, where t is the time spent in hours that they ran. The runner plans to go for 1.5 for a 1.5 hour run, graph the function and identify its domain and range. Okay, so again, I'm going to put in my axes, but when you think about it, this one is completely going to be in quadrant 1 because I can't run a negative amount of miles and I can't run for a negative amount of time. Okay, so what we've got is we've got time on the x-axis, we've got distance on the y-axis. Right? I know that because t is my independent variable. When I go ahead and start putting together a input-output table, I know that 0 time is 0 distance, so I'm going to start at 0, 0, and it's only going to go to the right. Okay, so whether the problem specifies the domain or the range, yes, absolutely. I know that my time has to be greater than or equal to 0, and my distance has to be greater than or equal to 0 because it's not possible to run for a negative amount of time or to run a negative distance. So if I want to graph the formula, I know right off the bat that 0, 0 is one of my ordered pairs. So this is going to be time and this is going to be distance. And let's go ahead and plug in a 1.5 hour run. So, and actually, my time has to be greater than or equal to 0, but it has to be less than or equal to 1.5 because I'm going for a 1.5 hour run. Okay, so I'm going to plot the two ends of my line segment. 0, 0 is where I begin, and my distance will be equal to 6 times 1.5, which would be equal to 9. Okay, so I know that let's go ahead and make these a little bigger. There's 1, there's 2. So at 1.5, I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's where I will stop. Okay, and there's my graph. Okay, identify the unspecified domain or range. Well, they didn't call it domain or range, but I personally believe that it was specified in terms of domain. Now the range wasn't specified, so I know that my distance is greater than or equal to 0, less than or equal to 9. So it actually would have been more proper for me to write this one, even though it is correct, to have written it that my time has to be greater than or equal to 0 and less than or equal to 1.5. Okay, even though that is proper, this is more correct. Right? It's not that one is wrong, but we generally want to make the values make sense in terms of where they're located. 0 is to the left of 1.5 on a number line. It's most appropriate in a compound inequality like this to make 0 to the left of 1.5. Okay, and what if the runner plans to run 12 miles? Well, if we go back, it's distance is equal to 6t. So let's go ahead and do that. If distance is equal to 6t, I'm still in the situation where I can't run negative distances or negative time. Let me just get these squared away, all right? And now what I've got is, in the last one I ran for 12 miles. In this case they're saying, or sorry, 9 miles. In this case they're saying I'm going to run 12 miles, so I need to know how long I'm running. Time is going to be equal to 2. So here's 1, here's 2. I'm starting at 0, 0, and we're going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what this changed is it changed the domain and it changed the range, which is typical. Normally, if my domain changes, my range changes as well. Not always, but normally. So if my domain now is that my time is greater than or equal to 0 and less than or equal to 2 hours, and my range is that my distance is greater than or equal to 0 and less than or equal to 12 miles. Okay, and that's section 3.2.